So in this video, we'll describe the interesting formula which is called the rank-nullity formula. And let's say now the matrix M has size m by n. You see, m by n. And I'm claiming that if you find the rank of M and also the nullity of M, if you add these two numbers together, it must be n. And please recall, is actually the number of columns of M, right? And let's look at some examples now. Please look at the current matrix, which is 2 by 2. So we expect that because now n is 2, we expect that if you add the rank and nullity together, it must be the same as 2. Can you verify that this formula is correct? So first of all, just like the previous couple of videos, we can do some row operations. For example, I can do row 2 minus 2 times row 1 to reduce the matrix to upper triangular form. And now you see, if you look at it this way, because we are in the triangular form already, so we understand that the rank of M must be 2 now. Because if you look at the row space, it is actually spanned by the two basis vector, which is the row 1 and also the row 2, right? And obviously these two vectors have different directions. So it gives us the two dimension of this row space. And basically, because this space is R2, the two coordinates exist in each vector. Basically, the row space is exactly the same as R2, basically. And because of the fact that the rank we understand, which must be 2 now. So it gives us the sense that the nullity must be 0, right? And please recall the meaning of zero nullity. It basically means the solution of the homogeneous system with the coefficient matrix M must have dimension 0. So I'm saying that this fact basically means the homogeneous system formed by using the M as the coefficient matrix must have a 0 dimension as the solution vector. So it means we don't need any parameter to write all the solutions down equivalently. We can say that this system must have exactly one solution. And in the homogeneous case where the right-hand side is all 0, exactly one solution basically means the solutions of the two variables must be 0. And of course, this fact can be verified quite easily because, for example, when you reduce the coefficient matrix by using the Gaussian elimination, you are having this, and you can easily solve this to get that the only solutions are the 0 solutions, same as what we get by simply look at the rank nullity formula, right? And let's look at another example now. So now you see I'm giving you a 3 by 2 matrix. To verify the rank nullity formula, it basically means if you add up the rank and nullity, we expect that is the same as 2. Can you verify that? And let's find the rank first. So you see, to look at the rank, which means we can look at the dimension of the row space, and we can do some row operation first to get such a matrix in the reduced form. And now if you look at the 3 rows, you can easily see that the row 2 and row 3 give us the same direction, right? So it means what? It means if you look at the basis vectors, which generate the whole row space, I can simply use row 1, row 2, or row 1, row 3 as the basis. Both choices are okay, and it means the row space, I can write it this way. It is spanned by two vectors as the basis, and because the row space now is sitting in R2, in the sense that each row has two coordinates, right? And because we know that the row space has two dimensions, which means that basically the row space is the whole thing, which is the whole vector space R2. And it means the rank is 2, right? The rank is basically 2, right? And let's write it here. To verify that our rank nullity formula is correct, it means you must tell me the nullity of the M is actually 0. Can you see why? Because to look at the null space, we have to look at the corresponding homogeneous system like this. And once again, you can do the row operation to get the reduced form like this. And I think to solve this system is quite easy because I think the second and the third equation are giving us the same information. For example, if you use the second equation, you get that this second variable is 0. And if you look at the first equation now, it basically means the first variable must be 0 also. So it means what? It means in such a linear system, basically the only solution now is the 0 vector. This is the system where exactly one set of solutions exists, right? Because we don't need any free variable like free parameter to describe the solutions, and we have only one point, which is the 0 vector here. it means our solution space has 0 dimension, right? So it means that the nullity is basically 0. And I can write it here. The nullity is 0. You see, it means when you add the rank and the nullity, of course, you'll get 2, right? That's the way to verify that our rank nullity formula is correct. And we can look at one more case. So you see, please look at the size of this matrix, and the size is 3 by 4. And it means the rank nullity formula should have something like the rank plus the nullity should be 4. Can you verify that such a formula is correct? And in this case, as usual, we have to reduce the matrix anyway, and maybe in this case, we can try to find the nullity. It's equivalent to look at the solution space of the homogeneous system, and obviously we can do the row operations now. So if you do the row operations correctly, you'll be arriving at this solution, at this linear system. And to solve this linear system, we can use the last equation first. That's for the second variable. So it means the second variable is actually 0, right? And then you can look at the second equation, which is something like this. And because now x2 is 0, we understand that the last variable is also 0, right? Now the only first equation remains. It's an equation that has 4 variables, but we have already verified that x2 is 0, right? And x4 is also 0s. So basically you have two variables left in one single equation, which means I can set maybe the last variables x3 to be t, and in that case x1 can be written as minus 3t, and it means all the solutions can be written like this. So you see, because you use only one free parameter to describe all the solutions, it gives us a sense that it's basically a one-dimensional subspace with basis vector like this in R4, right? Anyway, it basically means the nullity is 1. Because our solution space requires one parameter to write all the solution down, it means the dimension of the null space is 1, nullity is basically 1. And let's look at the rank of the matrix. And the rank, of course, we can look at the row space now. And because we have done the row operation already, we can single this matrix out. So you see, can you tell me something about the row space of this matrix? And I think it's quite clear that, you see, if you look at the row, the last row cannot be used to generate the second row because the second row has a non-zero spot in the last spot. And it cannot be generated by the last row anyway. And similarly, the row 1 cannot be generated by the linear combination of the last 2 rows, because the last 2 rows have zeros in the first spot and the third spot. But the first row, we actually have non-zeros here, right? So I think it's quite obvious that if you look at the row space, actually spanned by the 3 vectors here. And you see, because each row basically has 4 coordinates, it means the row space, of course, is sitting in R4, and it's a 3-dimensional subspace in R4. And the 3-dimensional subspace here has the basis by simply using the 3 rows as the basis vector. And what does it mean? It means our rank of our current matrix is basically 3, right? And please recall we have found it already that the nullity is 1. So you see rank plus nullity now is 3 plus 1, which is 4. So I think it's a verification that the rank nullity formula is correct for this matrix M. And that's the end of this video.